In this example, we have two blocks of mass M1 and M2 being pushed upward with this applied force here that's pushing at an angle alpha relative to the incline. The incline is making an angle theta with the horizontal. We are given the masses. One of them is 3 kilograms, that's the first one, and the second one is 2 kilograms. We are given the coefficient of friction between the ramp and either mass, and we are given the angles, this one here being 20 degrees and this one here being 55 degrees. And we are also given the applied force, the magnitude of the applied force, 90 newtons. The first question is to find the acceleration of the blocks. So here, notice that it's asking about the acceleration of the blocks. It is not asking a question specific to one of the blocks. It's a question specific to both blocks together. So it makes sense when we work the problem that we actually don't focus on the fact that it is made up of two blocks, but treat it as just a one block of mass M1 plus M2. We treat it as such, and then if for other questions we need to separate them, we will do that in time. But for part A, we're going to treat it as one block. In all problems dealing with acceleration or forces, we use Newton's second law of motion. Acceleration can be found usually by either using Newton's second law that says the sum of all forces is equal to ma, or by using kinematics. Here, we are not given much information to be able to use kinematics. So our only source is Newton's second law of motion. Sum of all forces is equal to ma. To use Newton's second law of motion, the rules, remember, you need first to identify your forces, draw a free body diagram. So first identify, then draw free body diagram, then resolve your forces into x and y components, and then solve. Okay, we need to do these 4 steps. Identifying the forces. So what are the forces acting on our blocks? Of course, we have the obvious one, F applied. They discuss friction here, so there must be a friction force. That friction force has to be opposite to the direction of motion. Since we are pushing this upward this way, you expect the direction of motion to be upward up the ramp. So the friction force is going to be in this direction, and it's going to be a kinetic friction force. So F friction kinetic. Then of course we have the gravitational force due to the earth pulling down on the masses, and that's going to be M1 plus M2 times G, using G as 10 newtons per kilogram. The masses are 2 kilograms plus 3 kilograms, so that's 5 kilograms. 5 kilograms times 10, that gives me 50 newtons. So we get it out of the way. Then there is the normal force that the ramp exerts on the blocks. That's the only forces acting on the blocks that we can think of, 4 of them. Now the free body diagram. free body diagram. Remember, your gravitational force is straight down along the vertical towards the center of the Earth. The normal force, we call it normal because it's perpendicular, so it's going to be perpendicular to the surface. And we have the other two forces. Now, notice that this here is theta. So this, since this is vertical, it goes straight down. This angle is the complementary of theta, so it is 90 minus theta. And the angle that the gravitational force makes with the perpendicular is just theta then. Okay, so our free body diagram, this is my x, which is parallel to the incline. We choose it parallel to the incline to simplify the math. Then this is my y-axis. So the gravitational force, if this is my y, this is my x, it is in the third quadrant here. Fg, with this being my theta. Now, the normal force is along the y. The applied force, this is my y-axis, x-axis. You see it is in the fourth quadrant. And this angle being alpha. And then the friction force is along the x-axis in the negative direction. That's my free body diagram. Of course, I don't have space here anymore. I'm going to redraw it quickly in the next page. So my free body diagram is Fn, F applied, Fg, and the kinetic friction. The sum of all these four forces is equal to ma. So F plus Fn plus Fg plus F applied is equal to ma. That's the way I'm going to find my A. Now I wrote my equation. Remember, what we need to do is resolve it into x and y components. So along the x-axis, my friction force is going to be just minus the friction force, minus the magnitude of the friction force. We don't know what that is. Fn has no component along the x. Fg is going to have this component along the x, so that's going to be minus, it's in the third quadrant, it's pointing in the negative direction, so it's minus the magnitude of Fg times the opposite to the angle theta, so that's sine theta. And then for the applied force, this is going to be the x component, so it is adjacent to the angle, so it's going to be the magnitude of the applied force times cosine of alpha. I'm running out of space, but that should be equal to m, which is the combined mass, times A. Let's rewrite this equation with the quantities that we know. We know that the friction force is related to the normal force by this expression. We'll apply that here. We'll write it down here. So that's going to be, since we are given the coefficient of friction as 0.2. our equation here becomes minus 0.2 times the normal force. I'm going to omit the 0 since it's a 0. And for Fg, we said it's 50 newtons. We calculated it earlier, so we'll use that. So 50 newtons sine the angle theta is 20 degrees. So it's sine of 20 degrees plus Fap, which is 90 newtons, cosine alpha is 55 degrees, and that's equal to 5 kilograms, the combined mass, times A. So this is one equation with two unknowns, Fn and A. So we need to write the equation along the y. The equation along the y, the friction is going to have no component. The normal force is going to be the normal force, the magnitude of the normal force. Fg is going to be negative, but it's going to be this component, so minus Fg cosine of theta. And the applied force is going to be again negative, but this component, which is minus Fap sine of alpha. And that's equal. We are not going to have any acceleration along the y, since our mass is going to just move along the incline. So that's going to be equal to 0. Rewriting this with the quantities that we know. So we have Fn that we don't know, minus Fg, that's minus 50 newtons cosine of 20 degrees, minus Fap, which is 90 newtons sine of 55 degrees, is equal to 0. Notice here that we have only one unknown, Fn. So we solve for it. Fn is 50 newtons cosine of 20 plus 90 newtons sine of 55. And that's equal, if I didn't make any error in my calculation, 121 newtons. That's my normal force. Now that I have the normal force, let me change the color of the ink. Now that I know the normal force, I'm going to plug it here. Okay, I'm going to rewrite this equation in the next page. Minus 0.2 Fn minus 50 newtons sine 20 plus 90 newtons cosine of 55 degrees is equal to 5 kilograms times A. Let's verify that. 0.2 Fn minus 50 newtons sine of 20 plus 92 newtons cosine of 55 is equal 5 kilograms A. And then we replace Fn by 121 newtons. So this is minus 0.2 times 121 newtons minus the 50 Newton sine 20 plus the 90 newtons cosine of 55 is equal 5 kilograms times A. So now all what we have to do is calculate all of these. As we calculate them, they come out to be 10 newtons is equal to 5 kilograms times A. So that gives me my A, 10 over 5, which is 2 meters per second squared. That's the answer here. For part B of the question, they ask us to find the force that block M1 exerts on block M2. So they are asking us for the force that this block exerts on this. To solve part B, I cleared my screen. I removed all the notes that I wrote for question A, so we can have plenty of space to work. Remember, from part A, we found that the acceleration is 2 meters per. So the acceleration, we found it as 2 meters per second squared. Okay, since I'm being asked to find a force acting on M2, I need to check all the forces acting on M2. What are the forces acting on M2? Of course, there is the gravitational force due to the pull of the Earth on M2. There is the friction force due to the ramp on M2. Again, it is a kinetic friction force. There is also the normal force that the ramp exerts on M2. And then, of course, the force that we are trying to find, it is also a normal force, because two surfaces are pushing against each other, due to M1 pushing on M2. Okay, so if I write them down, the forces are force of friction due to ramp on M2, force normal, let's call it normal 2, due to M1 acting on M2, gravitational force due to the Earth on M2, and the final one is the normal force of the ramp on M2. If we do a free body diagram, it's going to look like this. Fn is here, Fg is here, with this angle being theta. The friction force is going to be here, and Fn2 is going to be like this. Notice here that we didn't write the applied force. The applied force acts on M1, not M2. What acts on M2 is this push from M1 that we accounted for here. Okay, I'll redraw the graph in the next page. So again, y-axis, x-axis, Fn2, Fn, friction, and gravitational force. Remember, we know the acceleration in this case. We found it in part A. Both masses are going to move with the same acceleration. So my acceleration is 2 meters per second squared. Writing Newton's second law of motion, sum of all these forces is equal to ma. In this case, that's going to be friction force plus Fn plus Fn2 plus Fg is equal to m, which is the mass 2 times A. Now we need to resolve the equation. Along the x, the friction force is going to be 0.2 times the normal force with a negative sign, since it's pointing this way. The normal force is going to have no component along the x. Normal force 2 that's due to m1 is going to be along the x, so that's going to be plus Fn2. That's what I'm trying to find. Fg is going to have this component along the x, which is going to be minus m2g times sine of theta, and then we have that's equal to m2a. If we replace everything that we know, so minus 0.2 times the normal force plus Fn2 minus m2 is 2 kilograms times g, that's minus 20 newtons sine of 20 degrees, and that's equal to 2 kilograms times 2 meters per second squared, or 4 newtons. So you notice here we have two unknowns, Fn and Fn2. So we need to write the equation along the y. Friction force has no component along the y. Normal force is going to be the full Fn. Fn2 has no component along the y. Fg is going to have this component along the y, which is minus 20 newtons cosine of 20 degrees. And A has no component along the y. So in this case, my Fn is equal to 20 newtons cosine of 20 degrees, which is equal to 18.8 newtons. That's my Fn. So I'm going to take this and replace it here. I'm going to rewrite the equation on the top here. So that's going to give us minus 0.2 times 18.8 newtons plus Fn2, what we are trying to find, minus 20 sine of 20 and that's equal 2 kilograms times 2 meters per second, 4 newtons. Okay. The only unknown there is F sub n, so we just rearrange, move everything else to the other side. Sorry for the space here. So my F sub n is going to be equal to the 0.2 times 18.8 newtons. That gives about 3.8 newtons that we move to the other side, becomes positive. And then we have 20 sine of 20, 20 sine of 20, that comes out to about 6.8 newtons, and again it becomes positive since we move it to the other side. And we have the 4 newtons that was there to begin with. So the sum of all of these is our, actually this is normal force 2, by the way. That's what's left. So this is the force that's exerted by M1 on M2, which is 14.6 newtons.